Okay, so we've talked a little bit about intermolecular forces, the forces between molecules that kind of keep them together, right? And the stronger this force between them, the more likely they are to be a solid. If they don't have very much force between them, they're going to be more likely to be gas. And if there's some sort of medium amount of force, they're going to be liquids, right? But what we haven't talked about is how do molecules get these intermolecular forces in the first place? Why do some molecules and atoms attract to each other and other ones don't? So this video is going to cover one of those ways. So we're going to be looking at polarity, and sometimes called hydrogen bonds as well. So polarity is basically when you have a molecule and they're not sharing their electrons equally, right? So we can see we have an atom here, we see them playing tug of war between these two electrons, so you might recognize this as a covalent bond. And we've kind of said that they're pretty equal at this in the past. Well, it turns out not all of these atoms are perfectly equal at this. In fact, some are stronger at pulling on electrons. And then just a reminder, that's called electronegativity. So this atom is more electronegative, and this one is less. And so what happens is, as they're fighting over these electrons, the electrons kind of shift over towards the more electronegative atom. And so what happens is there kind of ends up being a slight negative charge over on this side because of the extra electrons around, and a slight positive charge on this side because there's still this positive nucleus, but the electrons are kind of over here now. So we get a little bit of positive here. And so this creates polarity. By polarity, we mean like a pole. So our atom ends up kind of having a positive side and a negative side. And what do we know about positive and negatives? Well, they attract each other, right? And positives repel. So this polar molecule can now go and attract to other polar molecules. So I have a little example here, right? So I have these polar molecules I've created, right? So we can see a plus and a minus on this one, plus and a minus on this one, right? So because they're charged, because there's a little bit of positive charge over on this side and a little bit of negative, when it finds another molecule just like it, now when it gets close to each other, they stick together, right? So there's some force holding them together, which means that this is going to have more intermolecular force, which means this is more likely to be a solid or maybe a liquid, depending on how strong. This one's kind of medium strength, right? Pretty easy to pull apart. So I would say this is probably more like a liquid, right? And if I had really strong magnets, that would be kind of like a solid. All right, so, and then of course, we should also keep track. What happens if these molecules meet? Oh, you kind of saw it right there, right? What happened? So if the positive end of one molecule meets the positive end of another, instead of attracting, they repel, right? So you can kind of see that, kind of fun. And then as soon as it hits that negative, boom, they're stuck together, okay? So these polar molecules are more attracted to each other, so the more polar they are, the higher their force holding them together, and the more likely they are to be a liquid or a solid. So that's what we mean by polar molecules, so exactly that. So how do we show this on our atoms? Well, what's creating that positive and negative charge, again, is this shift of electrons, right? So this is a cloud of electrons, and we can see this whole cloud of electrons has shifted towards chlorine and away from hydrogen. So we know a couple things. Chlorine is more electronegative than hydrogen. That's why the electrons are shifting to that side. And then we know that when you have extra electrons around, you get a little bit of negative charge. And that's really what this symbol means. It means a little bit, okay? So this symbol here just means a little bit of charge. Not a full charge, a little bit of charge. And so what we can see is we have some positive here and some negative here. So if you have another HCl molecule, the H of one can stick to the chlorine of another. So we'd call this a polar covalent bond. So it's still covalent, they're still sharing the electrons, but it's polar because it's not equally shared, right? And so we get these partial charges, little bits of charge. And then we can compare this. So now that we have the word polar to show unequal sharing, we can use the word nonpolar to show a perfectly shared one. Hopefully you can see why chlorine and chlorine would have a perfectly equal sharing, right? These are the same atom, so their electronegativities are identical, so they're perfectly even at sharing electrons. So they don't have any polar, positive or negative charges on them, right? Polar covalent would be small partial charges, right? Again, the electrons have shifted over this way. You can see the bulge of electrons and a little bit of a deficit here. And then compare this to our ionic bonds. Remember, this is when the electron completely leaves. So we have a big old electric cloud around chlorine, giving it a full negative charge, and some empty cloud around sodium, giving it a full positive, right? So remember, this positive and this negative are stronger than these partial negatives and partial positives. So these ionic bonds tend to form solids. Pretty much all ionic compounds form solids because there's a full positive charge and a full negative charge, huge intermolecular forces between them. Medium, so this would be a liquid possibly or a solid that melts easier than this one. And then of course Cl2 is chlorine gas, right? Pretty toxic gas, but it's a gas because when this Cl bumps into another Cl, it doesn't care at all. There's no attraction between them, or very little attraction. Here's another drawing showing these partial charges. And then here's the word, when it's a OH bond, we call it a hydrogen bond. So it's still a polar bond. Notice that oxygen is the negative side and hydrogen is the positive, so we can tell that oxygen is more electronegative. So these electrons have shifted over this way. And what that means is when you have two waters next to each other, the H of one will kind of be attracted to the O of another. Notice this intermolecular force is not a full bond. We show it with the dotted line, totally different than this. This is a complete bond. This is much, much stronger. So we call that intramolecular. And this gives water its interesting properties, right? It has surface tension, it has a relatively high melting and boiling point compared to some other compounds, and things like that. And here's the same picture, but showing the clouds of electrons, right? Remember, this is just a cloud with the blue showing that there's not very many electrons and the red showing a lot of electrons. And so we get a little negative, little positive, and they just kind of stick together like that. All right, so non-polar bonds. So again, anytime you have two atoms that are the same, so O2 or F2 or H2 or N2, right? Anytime you have two atoms like this, right, O2, F, H2, they have the exact same electronegativities, right, as each other. So they're both pulling on the electrons, but it's the exact same strength. And so it cancels out, right? Hydrogen is really weak, so I'm going to draw small arrows. But it doesn't matter. It doesn't matter how strong or electronegative or weak they are because they're the exact same elements. So it cancels out. So nonpolar, one way to tell is if it's the same atoms. Another very common nonpolar bond that I really want you to know, so I would recommend writing this down, is CH bonds. These are huge in biology. They're everywhere in biology, and I want you to know this is a nonpolar bond. So there is a difference in electronegativity, but it's very small, and so we consider it nonpolar. Okay, so that's nonpolar. So make sure you guys have these written down somewhere, right? Any two elements that are bonded together the same, or CH bonds. Those are going to be our main nonpolar bonds. Polar bonds is when there is a difference in the electronegativity, so there's an unequal sharing of the electrons. One side gets more of the electrons and one side gets less. So the one that's more electronegative is the one that gets more of the electrons, so it gets a slight negative charge. The one that's lower in electronegativity is the one that's kind of like letting go or losing some of the electrons, and so it gets a slight positive charge.